Hello ladies and gentlemen, we're going to do 1.1 to 1.3 today. We're going to be talking about limits, graphically, numerically, and analytically. So we are going to go back and kind of review the preview of calculus. We're going to talk about our limits graphically, numerically, and then we're going to evaluate some analytically. So as we do our notes like this, and we're covering multiple sections, I will tell you which section the notes are coming from. That way you can go back and know which section of the book we are coming from. So if you remember when we started calculus last year, we talked about there are two basic problems that we will spend a lot of time on. One of those is the tangent line problem. Okay, and just to talk about it, we're going to go back and remember some of the details. So let's say I have a curve and I have a point C, and then I have the function defined at that value. And I might want to be able to find the equation of the tangent line to the function at that particular point. So I have a variety of ways that we can do it, but if you'll remember, the first thing that we started with was using a secant line. So if I chose 2 points and I drew a secant line through the curve, and then let's say I chose another 2 points and I drew a secant line through the curve, and then I chose yet again another 2 points closer to the curve, right? Eventually, as I get closer and closer with my secant line, I can approximate the slope of the tangent. So I'm going to write that I can approximate the slope of the tangent line using secant lines that approach, I'll scoot it up in just a sec, that approach the C and F of C value. Alrighty, as the secant x's, so as I choose x values that are closer and closer to C, my secant line slope will very closely approximate the slope of the tangent line. And remember, and I know we did this for a long time last year, but we're going to go back and just talk about it again to make sure that you don't forget any of the details. The slope of any line is delta y over delta x. So now what we're going to talk about is my delta y's are going to be getting smaller and smaller, and my delta x's, okay, so if I chose this point right here, and I'll call this guy x1 and maybe this guy x2, and as those values, maybe x3 and x4, my delta x is getting smaller and smaller, where it's actually going to very closely approximate the slope at C. So that's our first problem that we'd like to talk about in calculus. The second that we'd like to talk about is the area under a curve. All right, and I know, again, that we've done all of these topics, which is why we're getting kind of an overview, and I'm doing 3 sections fairly quickly. So let's say I have a curve, and we'll call the curve F, and then I want to calculate the area under the curve from the points A to B. So I'm just going to kind of sketch this, and I'm looking for this area under the curve. Okay, so I'm going to talk about the area under the curve, and I'm going to do it in the interval from A to B. So I can estimate that area by drawing a series of rectangles. So I can estimate the area by drawing a series of rectangles. The cool thing is, and we discovered this last year, is the rectangles can all be different sizes. But depending on the location of the rectangles that I choose, I can either over or underestimate the area under the curve. Oops, I forgot the word under. Under the curve. So if I just go back and illustrate that, so let's say I chose this point and I drew a rectangle, and then I drew this point and I drew a rectangle, this point, and I'm going to draw a big one this time, and then this one up here and I drew a rectangle. If I summed up the areas, so if I called this area 1, area 2, area 3, and area 4, the area under the curve, I'll scoot this back up, would be equal to the sum from A1 to A4, and then that would equal my area under the curve. And if you'll notice the way I've drawn it, I'm slightly underestimating my area under the curve. I could choose different points and I could actually overestimate. And if you'll remember, there's a left, a right, and a middle, and we'll go back and talk about that ever so much more later. All right, that was 1.1 in a very quick nutshell. Now if we do 1.2, we're going to be talking about finding limits graphically and numerically. Because we are covering so many sections, your notes are going to be a wee bit longer each time, but remember that we will do problems from each of these sections for several days. Had to have a coffee break. All right, so a limit is a y value that a graph of f approaches as the x values move toward a point, and we'll call it C. Okay, and then remember that we move toward that point from the left and the right. Okay, so for example, let's say I have a graph, and it kind of does this, and then I have a gap, and then my graph keeps going. This is my C value, then the open circle would be my f of c, and then this is my function. So what we would say in our limit notation is that the limit of the function, I'm going to write it as f of x, as x approaches c from the right and the left would equal f of c. Okay, and if that point is undefined, so maybe that's a bad picture, maybe I'll fill in our little circle. If the value is defined, even if it's undefined, the limit can exist. And so we'll talk about several examples like that. So remember that if I write x approaches c with a plus, that means I'm coming in from the right. And if I write x approaches c with a minus up there, that means that I am coming in from the left. All right, so let's just do a quick example just to get your brains turned back on. And let's say I have a function which is x cubed minus 1 over x minus 1, and I want to find the limit of the function as x approaches 1. Okay? Well, if you'll remember, what happens is if I substitute a 1 in here, I get what's called the indeterminate, if I can spell it right, form, and I'll talk about that more in a little bit, but I get a 0 in the denominator when I substitute in a 1. And that's a bummer because the world wants to explode. So I'm going to rewrite this function by factoring the top. So I'm going to do, in case you don't remember, it's x minus 1, and then x squared plus x plus 1. Okay, it's a perfect cube binomial. And then the bottom is x minus 1. Well, these two little guys go away because it is removable discontinuity. We'll talk about that again more as we go along. Alrighty. So if I do that, now my function is a little bit more polite. So now I could take the limit of the function as x approaches 1, because there's no values in the denominator that make the function undefined. So this would be the limit of x squared plus x plus 1 as x approaches 1. And I'm going to get 1 squared plus 1 plus 1, so I'm going to get a 3. Alrighty? And now let's do this graphically just because we can. If I graphed this function, it would look something like that. At 1, okay, we know that as x approaches 1, that I have removable discontinuity, and then up here at 3, that would be my graph. Alrighty? Okay, so this value would be 3 that the graph is approaching. If x is equal to 1 and it's removable discontinuity, technically, my graph looks kind of crappy. I have a hole there. But as I come in from the left and as I come in from the right, I'm approaching that value of 3. So let me go back and remind you how to do this in your calculator. So I'm going to clear what I have, and I'm going to enter our function was x cubed minus 1 divided by x minus 1. And we want to show in our table that the limit actually exists, because if I look at the graph, I don't see my removable discontinuity. Let me make sure I entered that correctly. X cubed minus 1, I did. Alrighty, so I got just a cute little parabola. Alright, so I'm going to go to my table set, and I'm going to tell it to start at 1, because that's the limit that we're approaching. And I'm going to tell it to approach in point 1, and I'm going to look at the table. And I'm going to move up a little bit. Well, notice that as I come in from the right, as I get closer to 1, I have an error. Well, I have an error there because there's a hole there, because it was removable discontinuity. And if I come in from the left, I also have an error, same error, for the same reason. But notice that my values coming in from the left are getting closer to 3, and my y values coming in from the right are getting closer to 3, right? They're decreasing and approaching 3. But it's not definitive, so I'm going to go back and I'm going to change my table to start at 0.01. I'm going to leave it right here at 0.5, and then I'm going to go look at my table. Okay? Ooh, that's bad. Go back to my table set, and I'm going to start at 1 again. Now I'm going to look at my table. And notice it seems a little bit more clear, somebody loved me, that as I come in from the left, I'm approaching 3, 2.97, and then over here I'm approaching 3 as I come in from the right. So that would be my tabular confirmation that the limit of the function is actually 3. Alright, so let's go back and remember some details for a limit to exist. So for a limit to exist, and let me turn my phone off so I don't get any more surprises. Remember that the left and right hand limits must agree. Remember that the function must converge on a real number. Remember that oscillating behavior doesn't converge, and since it doesn't converge, then that would mean that the limit wouldn't exist. And then the last thing to remember is that a limit is unique at each point along a function, okay, or about a function, or whatever makes the grammar a little bit better. So remember that my limits are unique. All right, so just to get us thinking about our limits again, we're going to do an example. We're going to have a cute little graph. And I'm going to go out to 1, 2, 3, 4, 5, 6. Remember, I have to have arrowheads on each axis. And then I'm going to go up to 6, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5. This is a negative 5. I'm going to have a vertical asymptote at a negative 2. And I'm going to have a curve that goes here. I'm going to have an open circle that's at about a half. You have to pretend. And I'm going to have a curve coming in. Then I'm going to have a value defined at 1, 2, 3, 4. 1, 2, 3, 4. This value is defined. And at 2, it's going to go to 1. And I'm going to have an open circle. And then at 4, 2, 3, 4, I'm going to have a value of 2. Okay, so at 4 I have a value of 2. And then this particular section is going to go up. And this is going to go away. So that's our cute looking little graph. Now let's do some different evaluating. So let's say I want to do f of a negative 2. Okay, well at a negative 2 I have a vertical asymptote, so the function does not exist at f of a negative 2. Well then I want to talk about the limit of the function as x approaches a negative 2. Well, if I think about it, as I approach a negative 2 from the left, I would get a negative infinity. And as I approach a negative 2 from the right, I'm going to get a positive infinity. The right and left hand limits do not agree, therefore the limit does not exist. The next thing I want to evaluate is f of 0. Well, that's easy. F of 0 is 4, okay, because this one's undefined, so then that means that one is defined at 4. And then I'm going to say the limit of the function as x approaches 0. So then if I do the same process, if I come in to 0 from the left, I would get this value right here, which is about a half. And if I come into 0 from the right, I would get this value, which is 4. The values don't agree, therefore the limit does not exist. Okay? The next one we're going to do is f of 2. Well, I look at f of 2, and it's a really crappy drawing, but that's really supposed to be an open circle. So f of 2 does not exist. And then our next evaluation point, I want to do the limit of the function as x approaches 2. Well, if I come into 2 from the left, it approaches 1, even though it's undefined. And if I approach 2 from the right, even though it's undefined, they both approach 1. Left and right hand limits agree, therefore the limit is 1. If I do f of 4, I get the value 2. So then let's talk about what happens if I take the limit of the function as x approaches 4. Well, if I look at the function as x approaches 4, if I come in from the left, it's going towards positive infinity. And if I come in from the right, it's approaching a positive infinity. But by our rules so far, it says it has to approach a real number. Therefore, we would say the limit doesn't exist. If you'll remember from last year, eventually we will say that the limit approaches positive infinity because it's both approaching the same value. All right, so that was it for section 1.2. That was pretty fast. Section 1.3 is evaluating a limit analytically. So we're going to evaluate a limit analytically. But remember, we're going all the way back to the beginning, so you don't get to use L'Hopital's rule. Sad day. So this is a no-no for right now. We will go back and use it again later, but for right now it is a no-no. All right, so let's go back and talk about some properties that we need to remember. So if I have a limit of an f of x plus a g of x as x approaches c, remember that I can split that into separate limits and evaluate each piece separately. Right, so plus the limit of g of x as x approaches c. So that would be the limit, and I can split it into two potential pieces. I could also do the situation where I had the limit as x approaches c of f of x times g of x, not a dot product, but just multiplied. Then this would be the limit of f of x as x approaches c multiplied by the limit of g of x, oops, I need an extra parentheses, as x approaches c. So remember, it's really important that I need to do lots of things to help me evaluate a limit, and sometimes that means I can split it up into multiple limits. All right, remember when we are evaluating UAT, a limit, I have lots of different ways that I can do that. One of the ways that we really like is called direct substitution. So I can substitute a value into the limit and then come up with a mathematical solution. The caveat is that the world can't explode, which means that I have to have no indeterminate form. And if you'll remember from last year, that means that no rational functions. Because if I have a rational function, that means that the denominator has restrictions because I don't want the world to explode. So if I want to do direct substitution, I either have to not have a rational function or I have to eliminate the indeterminate form. But let's start off nice and polite. And let's do the limit of 4x squared plus 3 as x approaches 2. Again, this is not a rational function, so I have nothing in the denominator to make it undefined or the indeterminate form, so I can just do direct substitution. So this is going to be 4 times 2 squared plus 3. 2 squared is 4 times 4 is 16 plus 3, this is 19. Remember, we have to always be very careful with our notation and writing our solutions at the bottom of our work to make sure that our readers can understand what we're doing, and there is the limit of that particular function. All right. Let's do another example of a rational function because those have some interesting things happen to them. Oops, I forgot to change pins. So let's say I want to do the limit as x approaches 1 of x squared plus x, that's an x plus 2, over x plus 1. All right, so there's a lot of things about this particular rational function that we can remember. Number 1, I have a vertical asymptote at x is equal to a negative 1. The degree in the numerator is higher, so I also have a slant asymptote, so we're not going to talk about that too much right now. And then I can also evaluate the numerator, right, to find my zeros. So if you'll remember, the numerator would give us our zeros. Okay? So since I'm putting in a 1, that doesn't make my denominator undefined, so I can do direct substitution, which is really nice. So my limit as x approaches 1 of x squared plus x plus 2 over x plus 1 is going to be 1 squared plus 1 plus 2 over 1 plus 1. 1 plus 1 is 2 plus 2 is 4 over 2 is 2. And if you'll remember, if we look at this graphically, even though it's a rational expression, I had a vertical asymptote at a negative 1. And then as x approaches 1, so on this side of my function it's doing something like this, and on this side it's doing something like this, then right there, that value would be 2. And there's a slant asymptote in there which would be going this way, but for right now we don't care. Alrighty, so let's go back and talk about some trig limits. Okay. If I have the limit as x approaches c of the sine of x, well, if I just do, sorry, you can't see it, my paper's out of the way of my dots. If I just do direct substitution, then this is the sine of c. So whatever the value of sine is at that point, that would be the limit. Same is true for cosine, so the limit of the cosine of x as x approaches c, by using direct substitution, because cosine and sine aren't undefined anywhere. Got to move my little arrow, it's right in the middle of my stuff. Then I would get the cosine of c. And this actually works for all trig functions. You just have to remember that some of our trig functions have some vertical asymptotes. So just since we're talking about trig, let's go back and get a reminder. The sine of an angle is y over r, the cosine of an angle, x over r, and the tangent of theta is y over x. Okay? Then if I do my other ratios, my cosecant of theta is r over y, just its reciprocal. The secant of theta is r over x, and the cotangent of theta is x over y, just in case you forgot that lovely little bit of information. All right, let's do another example, and I'm going to do it over here in my little hole since I have some space. We want to calculate the limit of x cosine x as x approaches pi. So if we think about this, I could rewrite it, and I could split this up to be the limit of x as x approaches pi times the limit of the cosine of x as x approaches pi. But I really don't need to, because the limit of x, when I do my direct substitution, is just a constant, so that's going to be pi. And then the cosine of pi, and if you're not remembering your unit circle, remember that's over there, so the cosine is a -1, so the limit of the function as x approaches pi is going to be -pi. Well, that was really easy. Okay? All right, let me see if I can figure out how to get my paper back within his little dots, because it keeps seeming to run off the edge of the paper. All right, so let's officially remember about the indeterminate form. And that would be, and that's before L'Hopital's rule. Remember, before you can use L'Hopital's rule, you have to show that the indeterminate form exists. But you can't have an undefined situation like some number divided by 0 or some function divided by 0 when I do my direct substitution, because our world would explode. That would be a bummer. Or I can't get maybe infinity over infinity or 0 over infinity. It just doesn't work. So then you have to manage the given function to eliminate the indeterminate form. All right, we're actually cruising right along. I have about a page and a scooch of notes, so we don't have too much longer to go. So let's do an example. And this one is the limit of x cubed minus 1 over x minus 1 as x approaches 1. And we've done this one already, but I just kind of want to go back and remind you that this creates the indeterminate form. And we've already done this problem, so I won't redo it. But remember, the goal is to get rid of or eliminate that indeterminate form, and we often do that by factoring. Because factoring is our favorite F word, and it allows us to cancel numerator and denominator factors, and then I have eliminated the indeterminate form, and then I can do direct substitution. All right, so since we have to manage, let's remember some tricks. So I'm managing to get rid of the indeterminate form. So one of those tricks would be conjugates. So remember a conjugate, if I have 1 plus let's say radical 3, its conjugate would be 1 minus radical 3. So we often use conjugates to help us manage the indeterminate form. And I happen to have an example. So what if I have a limit as x approaches 0 of the square root of x plus 1 minus 1 over x And I can hear you saying now, oh yeah, fun algebra. Well, I have the indeterminate form because if I substitute a 0 in here, my world's going to explode. So to manage this one, it doesn't do me any good to multiply by x over x, so I'm going to multiply by the conjugate of the numerator. So I'm going to manage this by multiplying by the square root of x plus 1 plus 1. And remember, I can't change the value of the equation, but I can multiply by a very unique 1. Well, if I multiply on the top, and this brings up a good reminder, remember that you have to carry the limit notation through the entire problem until you get to the point of direct substitution. If you don't, you lose points. Well, if I multiply a conjugate on the top, I'm going to get x plus 1. And remember, the whole purpose of a conjugate is that the middle term goes away. So then I multiply these two, and I get a negative 1. And then in the denominator, I have x times the square root of x plus 1 plus 1. Don't distribute here, because if you'll notice, in my numerator, those two guys go away. Well, that leaves x over x, so these two guys go away. I would rewrite this one more time, so I have the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now I can do my direct substitution, and I get 1 over 0 plus 1 is 1, the square root of 1 is 1, plus 1, and I get 1/2. So that was actually fairly polite. Did I do my math right? Those went away. X's, I think I did. I did my notes wrong, but I got the rest of it right. Whew, sometimes you just don't know what happens. All right, so then I have another example for us. Do this one in another color so we don't think they're related. I want to take the limit as x approaches 0 of the sine of x over x. Well, remember, we had some special rules for that, and we know that this is 1. And then I have another little trig one, so I guess I lied. This really isn't an example. It's just a, oh yeah, do you remember? And then I have a limit as x approaches 0 of 1 minus the cosine of x over x, and this is 0. So those are just two special cases that you need to remember. So two special cases to remember. Alrighty. So now let's do another example. Sorry, we're going to actually do an example this time. And I want to do the limit as x approaches 0 of the tangent of x over x. Well, I already know that it's the indeterminate form because I can't divide by 0, right? So I know that I have the indeterminate form. So I need to fix it. I need to manage it to get rid of the x. So I'm going to do a little bit of math. First, what I'm going to do is I'm going to write this as tangent of x times 1 over x. Nothing illegal there. And then I'm going to rewrite tangent. So I'm going to write the limit as x approaches 0. Tangent is the sine of x over the cosine of x times 1 over x. Well, if I put these two little guys together, their limit is 1. So I'm going to rearrange this again. And I'm going to do as x approaches 0 of the sine of x over x times 1 over the cosine of x. And I'm going to do it like that. Okay? This goes to 1, which is very nice. The cosine of 0 is 1, so now I'm ready to do my direct substitution. And 1 over 1 is 1. So that was actually fairly polite. All right, I have one last example, and then we're done. All right, so this time, for our last example, we're going to do the limit as x approaches 0, and I'm going to have the sine of 4x over x. And this one is still the indeterminate form, but I have to do some creative math on this one, and I don't know that it's intuitive. So let's do this. I'm going to change this to be the limit as x goes to 0, and I'm going to multiply the top by 4, and I'm going to multiply the bottom by 4. A constant, if you'll remember, gets to come out front, So this is 4 times the limit as x approaches 0 of the sine of 4x over 4x. And it looks very similar to the last problem in that I have a sine of x over x, but what I'm going to do is let y equal 4x, so I'm going to rewrite it. So this is 4 limit as x approaches 0 of the sine of y over y. It's almost like use substitution, but not really. Well, we know that this goes to 1, so the limit is 4 times 1, which is 4. So the limit as x approaches 0 of my function is 4. So that was actually fairly polite. Alrighty, that's it for today. I will see you tomorrow.